Thank you. It's a pleasure to be here, and I'm actually curious who of you is actually Dutch? Wow, that's impressive. So, did anybody see this recent episode of Arjen Lubach about the Dutch power grid? I'm curious. Okay, some. Okay, he could do better. Okay, thanks. So, for the international audience, Arjen Lubach is a TV host, and he gave a very good summary of the state of the Dutch power grid. So, our power grid is being used way more heavily than it has been in the past. For example, we use now electricity to heat our homes. We use electricity to charge our vehicles. So the demand for electricity has gone up a lot. And on the supply side of electricity, we also are changing things. We're phasing out fossil fuels. We have less coal plants. All the nuclear plants in France are altogether somehow under maintenance. This is causing problems. And so we are increasingly more reliable on sun and wind, and that is causing more uncertainty. And so the power grid originally was not designed with this type of supply and demand patterns in mind. It was designed at a time that we did use fossil fuels. We had big power plants where we would transform coal or gas into electricity, and to match supply and demand, we just let these power plants go a little slower or a little faster. Consumers did not have electric vehicles, so the demand for electricity was quite easy, comparatively easy to predict. And these developments together are causing these problems. Of course, mathematicians knew about this already a long time ago, but they didn't listen to us. And so I have colleagues from the University of Twente, and I'm curious, is anybody here from Lochem? Nobody, okay. So in Lochem, they did some tests, and they baked 5 pizzas and charged 3 electrical vehicles, and it went wrong. That happened in an experiment in around 2016. And so, and that is the problem. Like when we say our grid is full, it means that if we add more connections to the network, we are risking the possibility of a blackout. And why does this occur? Well, if we add more connections, we overuse our network, and then something might break. So, for example, a line in the network might fail. As a result, all the electricity has to flow through other lines. Those lines get more overloaded. Some of those lines might also fail. And then in the end, you get a blackout. And the blackouts are, in a way, intriguing. It's somebody asked me, can you predict them? And my answer is, well, sometimes it takes 2 years to find out why a blackout even occurred. So the question generally is no. It's really unpredictable. And so, for example, a famous blackout was in the United States, where 55 million people got without power for up to 4 days. And it's also like, why did this occur? Well, in the end, they found out that it was due to a software error somewhere. And then a line hit a tree, it wasn't detected well. They started shutting down things preventively for the wrong reasons, and then the electricity was, I'm making a mistake. I wanted to point, the electricity was going, it was supposed to go like this, but it went suddenly across the other side of the Great Lakes, and then everything went black. And so blackouts are a bad thing, and we want to prevent them from happening. But unfortunately, they sometimes do happen, and sometimes now it seems that renewables are playing a role. For example, in southern Australia, in September 2016, they had a big storm, they had infrastructural damage, and then 3 months later, there was a heat wave. And in Adelaide, were you working there? Were you living there at the time already? Yeah, so they were like, Adelaide is like a very sophisticated, nice city, but for several weeks, every half hour, they shut down electricity in a neighborhood to make sure, so these were like controlled blackouts, which is sometimes called brownouts. And this is really a bad thing. And then renewables were being blamed for that. And you can say, well, maybe it was the wrong reason or the right reason. They ended up putting a very nice big battery, and that really improved things a lot. But unfortunately, they had again some issues a few months ago. So that's the point where is that, well, we need you can also say, well, Southern Australia is not well connected to other parts of Australia and they need to improve connectivity. Then the question is, who's going to pay for this? It's like a game theoretic problem. They first shut down the coal plant, then they ask their neighbors, do you want to share the costs of adding a line? But of course, then they didn't want to do that. So it's a difficult problem. How do you time it well? It's an enormous logistical problem. We do need to add copper, but adding copper is slow and expensive, and you need to get permission for that. And so maybe instead, we should not only add copper, but we should also use the copper we have already in a more clever way, using better mathematics. Maybe we should do that. So this is why mathematicians got interested in this. And so mathematics has been quite successful, actually, in designing and also in transforming existing networks. And not only mathematics, but of course also technological inventions. For example, you see here a container. The container really has made logistic networks more efficient. Why? Well, you can put any type of product you want in this container, and you can ship the container on any type of network you want. Sea, road, or train. It doesn't really matter. And so this is really flexible. So you have the global logistics network now has this very nice hourglass architecture. If you look like this, it's a bow tie, but I don't own any bow tie, so I thought hourglass is more appropriate. You have this hourglass architecture where all the physical details, all the different logistical networks are here, all the applications, the users, the companies who need to ship, transport things are here, and then here at the center are the algorithms, is the mathematics, together with this beautiful invention. Some people claim it's the invention of the century, but it's maybe a little bit of an exaggeration. So that's kind of like the core of the hourglass architecture, and it's very nice. Another example where we have seen this is the internet. We used to have phone networks. If the mayor wanted to call the doctor, like 100 years ago, you would get like a person on the line said, like, I would like to talk to the mayor, please, or vice versa. And then this was like a centralized control. It's extremely inefficient. Just imagine that suppose we need to do that now. If we call somebody, we get somebody on the line. That would be crazy. Yeah? But that's essentially what our current power grid still is. It's like the same as 100 years ago. In the internet now, we have much better architecture. We have a packet. The packet contains information. It's part of a phone conversation, or it's part of a file. It doesn't matter. All you need is a part of the information, and you have some information about senders and receivers. And then, so the packet here is in the middle, together with queuing network theory and other algorithms, especially the TCP protocol. It's a very nice, clever algorithm that makes sure that you avoid excessive congestion. And then everything works fine. And it is really a miracle. Like 100 years ago, if I wanted to open a hotel, I had to build it first. Now I just go on a platform and I fill out my name, and I essentially have my own private hotel. They don't. I mean, so it's really amazing. It's possible. Of course, in Amsterdam they don't like this because it generates too many tourists. But this is like an amazing possibility of the internet. And so the power grid is next. But the question is, what are we going to do here? But there is a vision there that, for example, I need electricity, and my friend has solar panels, and I need the electricity tomorrow. So why not have my friend send the electricity to me by email? And we send it to me by email, well, over a virtual line, over a virtual power line. And if my friend cannot sell it to me, maybe my friend wants to store the electricity in a virtual battery. So that's the idea, that we would like to have the power grid architecture in this hourglass way. That, for example, if there is a new physical idea, for example, hydrogen is here, or there is a new application on the user side there that you somehow disconnect it to through a clever virtual layer in a network. But of course, so that gives rise to the idea of digital energy. But digital energy sounds a little bit like an oxymoron. Can you really kind of pretend like the physics isn't there? And it's really dangerous to do this, of course. And if you want to do that, you need a mathematical proof that it exists, that it's possible. So I got intrigued by that, by learning the physics. Like when I was in high school, I must admit, I didn't study mathematics, I studied econometrics, but then during my PhD, that got fixed. But I did, partly that I do this because I was blowing fuses during the physics classes, like the practicum. I really was bad at it, so I thought better not study physics. So the problem, the physics can be very, very unpredictable. So I have here a model. This is the SciGrid model of Germany. It's you can find it on the web, and we did some tests on that. And suppose there is this red line here close to Hamburg that is breaking, that is overloading. So this can overload, for example, because there is a lot of wind here. So yeah. So the question then would be, so that line is going to shut down. The question now is which lines will fail next? And I didn't want to do a guess answer because there are too many lines, but the answer is that the lines in yellow fail next. And so this propagation of failures, you can think of it as an epidemic, and people have tried to use traditional epidemics models, but they really don't work. And the reason is very simple. Like if I sneeze, the three of you catch a cold from me because you're close to me. That's how epidemic models work. We saw that in some of the PhD talk. In the physics of in power grids, it doesn't work like that. You get really long-range propagation of failures, and so you really can have like a line failing in Poland, and then suddenly there could be a problem in Portugal. It's really anything is possible there. So it's really complicated. That makes the physics really complicated, and so therefore also like analyzing blackouts mathematically was considered to be kind of like difficult, but I was kind of like, I like a challenge. And so as a probabilist, what we typically do is like rather than just trying to understand how everything works mechanically, we try to find probabilistic laws. And what was known is that in the United States, they diligently collected data on blackouts, at least since 1991. And what they found there is that there is a nice statistical law for the size of a blackout, and it turns out that the statistical law for the size of a blackout is approximately the same as we see on losses on the stock market. It follows a Pareto distribution. And this distribution has the property that most of the losses are caused by the big ones. The small ones do not matter. And that's for a mathematical modeler a first good thing, because if you go through these data sets, you find out actually that there are like 1,000 documented blackouts which are the result of squirrels eating part of the grid or other animals. And as a mathematical modeler, we cannot put squirrels in our model. That's just ridiculous, right? So we just kind of ignore the squirrels. In any case, those blackouts are small anyway. We don't worry about them too much. And but then the question is like, why do these big blackouts occur? Can we learn something from it? And the good news there is that actually we found that the underlying physics is not that important. What is the most important thing, if you look at this from a macroscopic point of view, is that, well, the propagation of failures is extremely complicated, but you always end up in a situation where the network breaks into several pieces. One piece has a shortage, the other piece may have a surplus. Then the piece with the shortage, that's where the big losses occur. And then the biggest city in that region is kind of determining the size of the blackout. And it turned out that the sizes of cities also have this same statistical law, this Pareto distribution. And so that kind of has as a consequence that network upgrades not really going to solve the problem. At least like network upgrades are necessary to make things work well on the average, but you're always going to have big blackouts. What we found from the data is that, so the sizes of blackouts, we cannot do much about it, but we found that the duration, like most of the blackouts are rather short-lived. So maybe instead we should come up not investing all our money in adding more copper, but also invest money in adding local solutions. That's kind of the insight that it gives, because like what you want to do is be able to survive a blackout of 12 hours, for example. Like if you do that, then the disruptive nature of blackouts is going to be reduced. And in that sense, maybe it's an optimistic statement that we actually might do better if we have more solar rooftops, or our electric vehicle has a full battery. We can use that and we can survive a blackout, and we would have had problems in the past when we did not have this architecture. All right. So we derived these insights actually using extreme value theory. That is another mathematical theory that has been developed in the Netherlands for setting Dijk heights. So that's also another feature of mathematics, is that you develop a mathematical theory to solve a problem, and then you forget about it for 50 years, and then there is another problem that you can use it to solve. That's the beauty of mathematics, I would say. All right, I'm going to another problem, which is more, not so much about the blackout, but about a typical operation, and it's about electricity market. So here you see German spot prices over a period of a couple of years, and they fluctuate wildly. And this is like, and we have seen this recently, that prices, especially because they've gone up. And you can say, well, this is really a bad thing, and I agree, but at the end of the day, fluctuating prices are only a symptom. They are a symptom of congestion on the grid. And so what these electricity markets try to do is they try to set a price to balance supply and demand in such a way that the costs for society is somehow minimized. But this price setting, it's kind of like we don't have a benevolent dictator, thank goodness. We don't, so it's kind of like a distributed, decentralized way of doing this through a market where people are trading. And yeah, the problem is that if you separate this price setting from the physics, then you're not really being efficient. Like what you would like to do is you want to set the price in such a way that supply is equal to demand, in such a way that our network, that the state of the network, that there is not that the voltages and the line flows are all in safe regions. But this is where the beauty of math comes in, and also like the challenge is like, especially these equations for voltages give regions of this size. This is, for example, for a classic model of, it's from an old paper of Ian Hiskin's classic model for just two generators, and this is the feasible space of what you can generate in terms of electricity for voltage. It's really complicated. Just think about now the fact that I'm going to trade with my friend through email, and millions of people are going to do that. You get really going to get in trouble. And so like integrating these physical models better into the markets, it has been estimated that, for example, in the United States, you can save billions a year. And it depends really on the countries. For example, in the UK, it's kind of easier. As long as London is fine, they don't care. Maybe I'm kind of over-exaggerating here, but like Iceland is just a nice circle with a glacier in the middle. But like the United States is a complicated topology. So every country, but like it can really make a big difference. But fortunately, there is old mathematics. In this case, David Hilbert, in 1900, posed 23 problems. And the 17th problem of Hilbert says something about properties of polynomial equations. You don't have to know polynomials. All you need to know is that voltages actually have this structure. And the last 20 years, people have leveraged this insight and come up with new algorithms to solve these equations in a better way and to build better optimization algorithms. So the optimization, the last 20 years, people in optimization have made a lot of progress on this, and the first new algorithms are already being deployed in practice. For example, I think in Switzerland now there is a more sophisticated planning in place. So that's kind of good news. The bad news is that it doesn't scale yet to this vision that everybody can trade. And it is kind of like the vision that the energy transition, as we heard, like we're going to be more responsible for our own electricity supply and for anything, and but it is also kind of like it's a promise that we can all also reap the benefit, and we can all trade. And I'm kind of optimistic here because I think that from the internet, like if you see like what the internet is now compared to what how the phones worked 100 years ago, still, if we now all try to call our friends simultaneously, we would get in trouble. The networks, the wireless networks and the other networks are just not designed for that. We just have to fairly share all the resources. And so that's kind of like we're going to use mathematics to do this. But there are mathematical challenges there. For example, if you want to solve these planning problems here, you would like to solve them in such a way that privacy is preserved. So you need privacy-preserving versions of these optimization algorithms. And that's really challenging. But there are now nice mathematical models of what actually privacy means, differential privacy. And there are really lots of interesting problems and ideas surfacing there. And so there is like, if you're a student and you want to work on this, it's a great field to get to a career in. And I'm kind of optimistic. If I teach my classes, like 20 years ago, everybody wanted to work on finance, make money, and now like this seems to be a more popular type of application. So given that, I'm kind of optimistic that I would live to see the situation where the power grid works just as efficiently as the internet does today. Thank you very much.